I'm going to talk about the demonstration of quantum computing for molecular property. Mainly is a harmonic vibration frequency on an ISQ device with result agreement with experimental data. All right, so mainly I will talk about the variational quantum eigensolver method. So basically we have variational principle, and then so that means given a quantum system Hamiltonia, you can prepare any trial state, and then you minimize these Hamiltonia. What you get is always larger than the ground state. So you just choose any wave function you want, and then try to minimize it, and try to see how low you can get. Okay. So the first, for molecular system, and then we have Hamiltonia for electron. So we need to do a mapping from electron to qubit. And since once we have the qubit Hamiltonia, then usually number of molecular orbital you use will determine number of qubit you will use. And then for the real machine, usually we have ansatz. The ansatz means we want to prepare this trial wave function or trial state. So you just construct a unitary. This is a quantum circuit. You can have chemistry inspired or hardware efficient or heuristic ansatz. Then once you prepare the trial wave function, then you just measure it and to get the expectation value. In quantum computer, the expectation value is easy because you just prepare your state and then prepare a circuit. Then you run it and measure it. But for traditional computational chemistry, it's very hard because they need to calculate the wave function and then do the integration to find out the expectation value. But so that's why if you can use this quantum computer to measure the expectation value, is maybe you can get some advantage. So this is much of what I have said. It's just that for this prepare these answers, usually I just show you one of them is a chemistry inspired. There's a chemistry inspired. Usually people normally use CCSD, and there's a hardware efficient. Usually I will use some in our work here. We use this kind of a circuit, real amplitude. Okay, and then you prepare your Hamiltonia at some atomic separation, then you do calculate the ground state, and then for another distance, you need to calculate your Hamiltonia again, and then find the ground state. Then you map out this potential energy surface, and then the vibration frequency will be in the equilibrium point where the vibration frequency you can calculate there. Usually you just find maybe 5 points around the minima and then find out the harmonic oscillation frequency, vibration frequency. So in the early demonstration, for example, IBM in 2017, I put up this paper that calculated small molecule. And then later, because there's noise, and then they demonstrate, okay, if you do the error mitigation, then you can reduce the error and fit into this the curve. The curve usually is because they are using because of noise and the limitation, technical limitation. So usually they will use and because of traditional computational chemistry community, they use the Gaussian orbital and they use the minimal set because the technical quantum resource, so they just use this as an initial test. But the problem is, the STO3G, a minimal base set, usually do not yield accurate result compared to experimental data. But the problem is, okay, so to be comparable with the experimental data, a larger base set must be used. For example, in traditional computational chemistry community, if you want to have a result compared to experimental data, you usually need to use larger bases, so-called CCPVDZ bases, which is much larger than the STO3G. But it's hard because now you limit the number of qubits and the circuit depth. So even for simple H2 molecule, if you want to calculate the result comparable to the real experiment data, you need to use 20 qubits. And then the circuit depth usually is 10 to the 4. So that's still beyond the reach of the current NISQ device. So in our work here, we are thinking about, because you use this Gaussian orbital, if we represent a Hamiltonian using a complete basis set, it doesn't matter which basis set you use. But because now you do truncation, you only use finite number of orbital. So that means the choice of orbital will determine the quality of your Hamiltonian use. Because now our question is, we want to use the minimum number of the orbital and then still have accurate representation of the Hamiltonian. So that's our goal, okay. So the answer would be, we probably should use another basis set rather than Gaussian orbital. Why traditional quantum chemistry community, they want to use Gaussian orbital? Because classical computer, they need to do integration quite often. Then a Gaussian orbital can give you the analytic result for integration and also differentiation. So they can do it very efficiently on classical computing. But quantum computing, as I said, we don't do integration, we don't do differentiation. We just prepare the measure. So we don't need to use Gaussian orbital. So in other words, we try to represent this Hamiltonian in a small number of orbitals, so smaller matrix. But most of the Hamiltonian, the important term, is already in those small number of bases. Then we can have a very accurate Hamiltonian. Then we can make a good prediction, only use minimum number of qubits. If your qubit number is reduced, then the circuit depth also reduced. So what kind of basis? We are using this Dobetchi wavelet basis. This Dobetchi wavelet basis has this advantage. You can have this. You can divide this real space and also basis set wave function approach the basis. So you can define this as fine region. Then you need more grid point, and for this you can use coarse region. You use less function to represent it. Because of the limit of time, I don't have time to go through this method. I just tell you that we are using this wave function, the Dobetchi wavelet molecular orbital. So this orbital can generate from the free software called BigDFT. So we try to use this one, and then using the minimum base set for using this Dobetchi wavelet-based molecular orbital for these three molecules. Then we only use the minimum base set, so that means the number of orbitals is small. It simulates STO3G, minimum base set. Then we can have accuracy comparable to real experimental data. Okay, but later we are trying to say, okay, we have done this for this small number of molecules. Then we are trying to find the row 1 to row 4 for all most of these diatomic molecules. So we consider 43 diatomic molecules. And then we try to use our original method. And then it turned out that the original method has some constraint, okay? So it does not apply to all of these 43 because other molecules may have some correlation which is not considered in before. So then we propose a method. It's called, we still use the Dobetchi wavelet basis set because it already gives us a very good result. And then second, we tried, because we are only using the small number of orbital to capture the whole, the quality, the high quality of Hamiltonian, but still there are something missing if you only use the Hartree-Fock orbital. So we are using Kong-Xiang orbital, molecular orbital. So that means we introduce exchange functional into our basis set, so that using the small number, we can get a more accurate result. The other one is when the molecule become big, then number of qubits also become larger. So we also using this first order independent electron pair approximation criteria to do the active space selection. So in other words, compared to this CCPVD design, they need 20, hydrogen need 20 to 60. In our case, we reduce in only 2 to 12. So we can use 2 to get hydrogen atom accurately compared to experimental result, and to other 43 molecules as well. So this is the active space selection criteria. And then this is our the 43 molecule we consider. And here you can show that, here we only use 2. Here it has 10. 10 means orbital, the spin orbital multiplied 2, so it's 20. And similarly like this, so we can significantly reduce the number of qubits. This is another method we are using to comparison. Here we just choose these 3 molecules, and then our method is number 3 here, which is based a smaller error in this comparison. And this is our method we propose compared to this CCSD method plus the single and double excitation plus triple excitation as a perturbation. So this method is now is the gold standard method in quantum chemistry. What is the gold standard? So that means usually you cannot do better than this. So you can see the root mean square error is comparable to this gold standard method in quantum chemistry. So if you look at this chart, so this one is the experimental value, this is a theoretical value. Then you can see this is our method. This is, okay, maybe this one is more easy to see. This is our approach. This is CCSDT. They are using very large basis, CCPVDZ. Then we only use our qubit is less than minimal basis set orbital, because we reduce from 60 to 12. So there we run this in using this some UCCSD. Then we find that some of the result is not good compared to experimental data. So we think because this is numerical, so we went on to go calculate this using the real amplitude answers. So that means here is number of the layers. So this is the first layer. Number of layer you repeat is 30, and then this 99 is the depth, circuit depth. So we found that within 100 circuit depth 100, most of them can have a result comparable to experimental data, and then the real amplitude outperforms some of the molecule in the UCCSD method. So we are hoping that okay, if we have we can have a device who can run 100 circuit depths, then we probably can implement this into the real device. But then later we're thinking about, can we still run this and then reduce the number? Okay, so we pick 3 molecules, H2, LIH, and the PN, and then we test what the circuit depths we need. Here it only needs 4, 12, and 35. And then 35 is still too deep. So then we are thinking about, and then if we want to calculate the vibration frequency, we need to have several points. So that means we need to calculate several points in order to calculate vibration frequency. So we are using another method to combine the quantum machine learning, unsupervised learning, with this VQE. So that means we will input the band length, and also because 35 is still too deep. So what we do is we use this measurement result feed-forward scheme. It's like the neural network. Usually we have this nonlinear activation function in each neuron, but in quantum mechanics, we only have a unitary to prepare this. Unitary evolution is linear. There is no nonlinear function, but quantum mechanics provide another thing, because when you do the encoding, you're already nonlinear, and also other scheme. So we are proposing, we are using, instead of repeat the circuit many times, we are doing here. We cut it down in here. We do the measurement first, and then feed forward the measured result to the next layer. And then finally, then the whole thing do the optimization. For example, in this case, for the LH, this K means the there is one measurement here, 2 layers, and one is within each layer, the unitary only 1 layer. Okay. Usually you can use 2 or many. So K and M, they are combination you can choose. So the result is this. So we only calculate this, the red point, then we can make out all the potential energy curve, very accurate, within the chemical accuracy. You can see here, this is within the chemical accuracy. And then for vibration frequency also, we only calculate the 2 point, this 2 point, and then this star is predicted by the machine learning. So then, what we get is this, okay. So for these three, what we get is the error compared to exact diagonalization, compared to experimental data. This is what we get, okay. And then, finally, here is, we have also some other work on how to encode the qubit efficiently. And then, the work here, we are in a preparation for publication. All right, thank you.